In this video, I'll show you how to solve the ALEKS problem called writing net ionic equations. To help you solve this problem, you're going to want to have a periodic table handy, and you're also going to want a table of polyatomic ions. This table of polyatomic ions comes from the website Socratic.org. So what we're looking at here is called a molecular equation. In order to convert it into a net ionic equation, our first step, step number one, is to break apart all of the reactants and products that are in the aqueous phase. So for us, that is both of our reactants and one of our products. So we're going to go through and we're just going to find everything that is aqueous, and we're going to break these substances apart specifically into their cations and anions. And we're going to write them as individual cations and anions instead of writing them as overall molecules. So this is where the periodic table comes in handy, as well as the table of polyatomic ions. When we're looking at a molecular formula, if we can see 3 or more different types of atoms, not quantity, but different types. So we have tin, we have sulfur, we have oxygen, that's 3 different types. If we can see 3 or more different types, then we know that we are looking at a molecule that contains a polyatomic ion. The atoms in a polyatomic ion stay together, which means that the polyatomic ion is either SNS or it is SO4. So this is where we're going to go to the table of polyatomic ions, and we're going to look for either SNS or SO4. We're only going to be able to find one of those because one of the combinations is nonsense. And here is the combination that we find. There is our polyatomic ion. The polyatomic ion in this compound is SO4 2-. Now this is going to help us make a prediction about the charge of our cation. Our cation, tin, we know needs to have a 2+ charge. The reason that I know that is because this molecule contains, or this compound contains, one sulfate ion, which has a -2 charge. I know that the cation's charges need to balance out with the anion's charges. So since this is a -2 ion, I know that this tin needs to be a +2 ion. And so remember, what we're doing here is breaking this compound apart into its cations and anions. I'm just going to begin by writing in this box down here. I have my tin 2+ ion. Don't forget to include states. That makes these problems really tedious, but they need to be included. And then my other ion, the sulfate, SO4 2-, also aqueous. So I'm done with that compound. And now I'm moving on to my next compound. This I have K2S, potassium sulfide. Here I can see a total of only 2 different types of atoms. When I have only 2 types of atoms, that means that I am not dealing with something that contains a polyatomic ion. I am dealing with a simple ionic compound. Potassium is my cation, the sulfide is my anion. I do still need to be able to successfully and correctly predict the charges on these 2 ions. To help me predict the charges, I'm going to remember this handy little trick with the periodic table. Everything that is in the first column on the periodic table forms +1 ions. This next column forms +2 ions. And then we have +3, skip the next column, -3, -2, -1, skip the next column. And then these guys, the transition metals, they just form all kinds of different charges that we can't really predict by looking at their location on the periodic table. So since I have potassium, which is in a predictable column, +1 charge, I know that this potassium ion has a +1 charge. From this little 2 right here, that is telling me that I have got 2 of those potassium ions in that compound, and I'm going to include that in my balanced or my net ionic equation. So I've got the 2 there because there are 2 potassiums in this formula. My anion, the sulfide, this is also one on the periodic table that sits in a column with predictable charges, the 2- charge. So I know that my sulfur here is a 2- charge, and I'm going to include that as well. So those are all of my reactants. That's pretty bulky. Now I'm moving on to the products. In a net ionic equation, I am working on breaking apart substances that are aqueous. If you have something that is in the solid state, like I do here, SNS, we don't make any changes to that formula at all. So we're just going to copy that, SNS, no changes. And then we move on to our final product, which is K2SO4. That is aqueous. That means I need to break it apart into the cation and anion. Now, I've already done the hard work of figuring out the charges on the potassium ion as well as the sulfate polyatomic ion, so I don't have to go through that process again. I know that I've got 2 of those potassium ions. Don't forget to write down that they're aqueous, and I need to make a little bit more room here. The 2 comes from that 2 right there. And then I also have the SO4 ion with a -2 charge, and that's aqueous as well. So what we're looking at right now, all of this that I've just written out right here, that is called a total ionic equation. Is not what the problem is asking for. The problem just wants the net ionic equation. To convert this total ionic equation into a net ionic equation, we've got to take one more step, and that is to cancel or cross out or delete, erase, whatever word you want to use, anything that is on, or I'm going to say any ions that are on both the left side and the right side of the equation. So anything, basically anything that is not undergoing any kind of chemical change. So for example, I have got the tin 2+ ion on the left side. If I look over on the right hand side, I do have tin, but I do not have the tin ion on the right hand side. It is embedded in this ionic compound. I have the sulfate anion on the left side, and I also have a sulfate anion on the right side as well. So that is something that I'm going to cancel out. I'm just going to cross that right out. I have the potassium ion, 2 of them on the left and also on the right. So those are going to get canceled out as well. The sulfide ion is on the left, but not as an ion on the right-hand side. So this takes us down to what we refer to as the net ionic equation. And what I'm going to do is just erase this stuff that we canceled out just to kind of make it look a little bit cleaner. And we'll just kind of squish this together. Clean up one more thing there. This is the net ionic equation.